Welcome to this tool demonstration for FTS for VMC. I'm Giordano Scarso, one of the project developer. In this video, I'll show you how to deploy and use FTS for VMC, as well as introducing some key concepts required to better understand the whole process. The source code is available on the GitHub page, while a pre-configured Docker container is available on Docker Hub. FTS for VMC is a Python-based research tool developed using the Flask framework. The main purpose of FTS for VMC is to enable the verification of properties on feature transition system in a family-based manner using the variability model checker. The variability model checker is a verification framework for definition, exploration, analysis, and model checking of system designs representing product families modeled as a parallel composition of sequential terms. To obtain the source code, we can either download it directly from GitHub as a zip file or cloning it using git and the clone command. Other software required to deploy FTS for VMC are graphics.to render graph and the Python interpreter to execute the code. While installing Python, it is also required to install the Python package installer to download other dependencies. After installing the required software, we can enter the folder containing the source code. We then create a virtual environment using the Python virtual environment module to prevent damaging a system-wide library. After creating the virtual environment, we can activate it on Linux by executing the activate binary. And now we can see that we are under the virtual environment. Since we are under the virtual environment, we can use pip install with the R option to install the requirements needed for FTS for VMC. This will now download and install all the required package. To execute FTS from VMC, we need to tell to the Flask framework where is the application. This can be done by declaring an environment variable called flask_app and assigning the path to fts.py. After that, we can run FTS for VMC by executing flask.run. And we can see that FTS for VMC is now running. Another deployment option is by using the Docker image on Docker Hub. This can be done using the following command. And by opening the provided URL, we can see that now we have an instance of FTS for VMC running. For Linux, Docker can be installed through the package manager or by manually building the program. For Windows and Mac is required Docker Desktop, which is available on the docker.com site. After installing Docker Desktop, we can execute FTS for VMC by opening the command terminal and by executing docker run with the repository and the Docker Hub. Since it can find the image locally, it will start downloading from the Docker Hub repository the Docker image. Now that we have a running instance, we can use a browser, and by visiting localhost with port 5000, we can see that an instance of FTS for VMC is running. We can see the example FTS is loaded, and now we can try uploading a .source file. We can see that the model is now loaded and the graph is rendered. Now that we have a FTS for VMC instance running, we can see an example of feature transition system by clicking on the Graph tab. This is an example of FTS. A FTS is a formal model that describes in a compact manner the behavior of all products on a software product line. FTS are defined as an extension of labeled transition system. Let's see how LTS is defined. This is an example of the labeled transition system. A labeled transition system is defined as a quadruple of elements. The first is a set of state, which we can see highlighted in blue. We have a initial state, in this case is 1, a set of action describing the transition, and the transition is itself, which can be used to pass from a state to another. Feature transition system expand the labeled transition system by adding a set of features, which they can be selected or not selected, a set of feature expressions that are added to the transition to determine whether the specific transition is inside a product, and a feature model that describes all the valid products. A product is a configuration of feature, and given a feature transition system, one of its products is determined by which feature expression are true, given a configuration. For example, this is the labeled transition system derived from the previous FTS, where we decided to select the feature S, which stands for soda, and the C, which stands for cancel. So we have a vending machine which distributes soda, and an order can be cancelled. And we can see that all the transition about serving tea are removed, and also all the transition concerning the free distribution of the drink. FTS for VMC take as input feature transition system described through the graphics.for file format. We can see, for example, the feature transition system describing the vending machine software product line. To upload a model, we need to click on Select FTS Model to select a .file. After selecting the file, we then click on Upload Model to send it to the application. Example of feature transition system in .dot format are available in the repository inside the test folder under the .dot folder. Given an FTS, we want to verify properties that are valid for all the possible products of the software product line. The usual approach is to generate every configuration and then verify the given property. A family-based approach uses the FTS structure to check a property in a single pass, skipping the generation of all the products. To do so, we need to ensure the FTS liveness, meaning that it does not contain deadlocks. Inside a labeled transition system, a deadlock is a state without an outgoing transition. Because of the variability of FTS's products, a state that is not a deadlock in the FTS can become one inside of a product. These are called hidden deadlock. Other than hidden deadlock, there are two ambiguities that can be found inside a feature transition system, which are dead transition and false optional transitions. A dead transition is a transition that is not reachable in any of the FTS products. A false optional transition is a transition that is not dead, it is not annotated with the feature expression true, and it is present in all the FTS products in which its source state is present. FTS for VMC can detect such ambiguities and report them back to the modeler to fix them. Alternatively, it can use automated resolving strategies. By clicking on Full Ambiguities Analysis, we can look for all the three types of ambiguities, while clicking on Liveness Analysis will only look for hidden deadlock to check if the FTS is live. Dead transition can be safely removed from the feature transition system since there is no product that can reach it. False optional transition are converted into mass transition by replacing the feature expression propositional formula with the constant true. Hidden deadlock can be solved by creating a new explicit deadlock state, not previously present inside the feature transition system, and for each hidden deadlock state, adding a new transition with the state as a source and a new explicit deadlock state as target, unlabeled with a new action not present in the previous set of actions, and by a feature expression that negates the disjunction of the feature expression of all its source states outgoing transition. On FTS for VMC, after a full ambiguities analysis, ambiguities can be removed by clicking on Remove all ambiguities. After clicking on Remove all ambiguities, we can see a preview of the new feature transition system. By clicking Apply, we can make the modification permanent. We can also choose to remove only false optional transition, which create a new preview, or remove that transition and hidden deadlock state. These two types of ambiguities are removed in the same operation because the removal of that transition can solve hidden deadlock. And by clicking on Apply Transformation, we can make the edit permanent. We can see, for example, on the feature transition system of a vending machine that all the false optional transitions are highlighted in green. As we can see, the transition between states 1 and 2 require a feature expression by not selecting F, which stands for free, and we can see that if the feature expression of transition 1 and 2 is true, then the transition between 2 and 3 is a false optional transition because it will always be executed. Similarly, with state 3, we transition between state 3 and 4, and transition between 4 and 1. This is a featured transition system describing the software product line for a mine pump. By clicking on Full Ambiguities Analysis, we can see that it has some ambiguities, such as some false optional transition, and in S20 a hidden deadlock. By clicking on Remove Dead Transition, we can see how the hidden deadlock is solved by adding a new explicit deadlock state dead and a new transition with action dead, and as feature expression the negation of the disjunction of the feature expression of the other outgoing transition from S20. Now that we have an unambiguous FTS, we can verify property with VMC. Since VMC works with modal transition system, that is a LTS that distinguishes admissible, necessary, and optional transition, such that by definition all necessary and optional transitions are also admissible, FTS for VMC converts in background the feature transition system into an MTS. This can be easily done by considering all feature transition system must transition as a necessary transition, its feature transition as an optional transition, and all its transition as admissible by removing feature expression. On FTS for VMC, this can be done by clicking on View Modal Transition System, and we can quickly change between the modal transition system and the feature transition system. We can see that transition with feature expression 2 get converted into mass transition, while transition with feature expression not equal to true are redrawn with dashed line, indicating that they are optional. Based on results from previous paper, we know that any formula expressed in VACT live box that is valid for a live FTS is also valid for all of its products, enabling the verification of a property in a family-based manner. After removing all the ambiguities from the feature transition system, we can now finally verify property in a family-based manner. We can, for example, verify that every time a open action is executed, which we can see is between state 7 and state 8, in the future there will always be a close action. By clicking on Verify Property, we can see that the property is true for all the MTS variant. Another example of property that we can check, we can verify that every time a pay action is executed, in the future we will execute either a take or a cancel action. By clicking on Verify Property, we can see that this formula is also true. If we replace the OR with an AND, the formula became false, and by clicking on Show an Explanation, the FTS for VMC provide a counterexample where we can see that the property is false. For example, here we execute a pay action and a cancel, and we close the loop, but a take action is never executed. If the formula inside the text area contains some syntactical error, for example, here the operators is wrong, we can see that by clicking Verify Property, the FTS for VMC informs us that the formula contains an error. FTS for VMC is built on top of two important software, which are the Python Analyzer that can detect ambiguities inside the feature transition system, and the Variability Model Checker used to verify property in a family-based manner. We can now see the analyzer in action by executing the command line interface version of the analyzer and by passing as an argument the path to a .file containing a feature transition system. We can see that the vending machine is live and it has a couple of false optional transition. Now trying with the mind pump model, we can see that it is not live. It has the hidden deadlock in the state S20 and it has some false optional. By passing the option hdead, we can skip the control for false optional transition, and we can see that the mind pump is not live and the false optional transition have been skipped. Now I show what the new feature introduced by FTS for VMC, which is the disambiguation using the ambiguities reported by the analyzer. And we can see, for example, the command line interface that return a new vending machine written in .language with the false optional transition solved, and as they are now must transition. The translate.py enable us to convert the newly created FTS into a modal transition system in the format accepted by the VMC. We can now see that the translation result inside this txt file. Finally, we have a prop file containing the property that we want to verify using the variability model checker, and by executing the variability model checker and passing as arguments the modal transition system and the property we want to verify, we can see that the formula is false. We can see that by executing VMC and passing the model as an argument, if we try to verify the property with the OR, we can see that it reported that is true, and if we try to report the formula with the AND between take and cancel, we can see that it is false, and by asking why, we can see the counterexample that FTS for VMC generates the graph. Thanks for your attention.